lunch. I'm Preeti Jagnani and I'm also representing King's College. Now I'd like to call Mr. Nripesh Parajuli for the session on probability and statistics. Nripesh is a PhD and has been involved in making healthcare AI products with Caption Health over the past 5.5 years. He was involved in developing the first FDA-cleared real-time guidance technology that assists non-expert users acquire diagnostic quality cardiac ultrasound images. Currently, he is working on a similar product for lung ultrasound imaging. He, he has a background in machine learning, biomedical imaging, computer science, and electrical engineering. A jack of all and a master of none, he enjoys working at the intersection of healthcare, technology, and society. In his free time, he enjoys watching and playing football. Thank you.
Thank you for the introduction. Can you all hear me okay? Yes? No? Okay. So, alright, as the introduction said, I'm interested in football, so I'm using football examples.
Manual focus myself.
So, if you know these guys, then I think what you're seeing here will kind of make sense to you if you like football and if you have some general idea. Kevin De Bruyne, he's a very good player. I think we can agree that, most of us here. And he's quite accurate, as you can see. So, caveat is I'm not using a football goalpost because it's a bit weird in shape and there's a goalkeeper in the middle, so I'm kind of using a dart board as a representation for conveying similar ideas. So forget about, you can think of this as dart. Maybe these guys are playing dart, but they have the same performance in dart just the way in football as well. So even in dart, De Bruyne is very accurate, hitting towards the middle. Arjen Robben, who he's retired now, but if you guys are a bit older, then maybe you know him. He was very good at shooting towards the left side, and he would always score, no matter what you tried to do to stop him, right? Bruno Fernandes, I mean, he sort of, in general, he shoots towards the middle, but he's also a little bit all over the place. He's not, you could say, as precise as De Bruyne. Antony, another player, a young player from Manchester United. He's trying to be like Robin, trying to be very good at shooting on the left side, but he's not there yet. He's maybe many years away. Maybe 5 years later he'll be as precise as Robin as well. So I mean, looking at this sort of can anybody tell me what is this kind of representation called? A word for this? Distribution. Did I hear distribution? That is correct. So we can say this is a distribution of shots taken by these footballers. Again, and you can think of this as dart or football or whatever. But like I already said, it's just a little bit easier to draw these pictures and make some modeling for darts than football. So you might ask then you might say, okay, why is this interesting? Why do we care about that? Why are we studying probability? Like I think it's pretty intuitive. Some of the things that you can infer from here are pretty intuitive. You don't really need mathematical modeling, right? So what are some things that you can intuit from here? Very, very obvious. Can somebody give me something? If you don't speak, I'm gonna point towards you, and you have to speak. So please, either volunteer or be forced. Any volunteers? Our friend here, we were talking earlier. This guy, he's wearing glasses, blue jacket. Oh, yeah, you can go ahead. Sure. So yeah, what are a few things that you can just tell about this data? And if you're a football coach, what would you say?
So the players at the bottom have higher variance in the distribution.
Right. That's a nice. That's a very good thing that you've got. Yeah. And what about the players on the right? How would you describe them?
So the mean in a sense is towards the left.
Yeah. And what is that term? bias. So these two terms are very important in statistics and particularly machine learning. Bias and variance. And maybe other speakers will continue talking about this. There's always a trade-off between, well, before we get into the trade-off, so what can you say about bias and variance? Like, what is it good to, is it good to have high bias, high variance, low variance? Who would like to guess? Or they know already, so maybe it's not guessing. Again, if there are no volunteers, I'm just gonna force you guys, so just maybe you should volunteer. Low bias and low variance is good. Yeah, I think that is correct. Can you maybe elaborate a little bit more? Yeah. Right. Or in other words, to simplify, you can say if the variance is low, the player is reliable, right? You can say, and again, if you know football and if you know these guys, Kevin De Bruyne, very reliable when he shoots. Oftentimes he's hitting towards the goal, right? Either the goalkeeper stops or he scores, right? Bruno Fernandes, not so much. There's less. They both have low bias. They're sort of both hitting towards the central area, but one has more variance and one has low variance. So which one is good again? Low variance or high variance? Everybody. Now what about bias? Is low bias good or high bias good?
Low bias.
Low bias is good, right? Because obviously we're trying to hit towards the center. If there's some guy who's always hitting to the left, that's also not like a great scenario for the coach, right? If he's trying to decide who should take the next penalty or something. So I think some of these things are, you don't need math to understand these things because we have so far zero math right now, right? So for what would you need math? I think that's what I'm trying to motivate. And I think statistical thinking and modeling helps with these kind of scenarios where the answers are not so obvious. Now, if I ask you, okay, it's clear that if De Bruyne is the guy you want to be taking your penalties, free kicks, whatever, right? If we follow this line of thinking. But what about between Robin and Bruno Fernandes? Who do you think is better? Is it obvious? Like, who should be taking your free kicks or penalties? Who do you choose? Anybody has an idea?
Bruno Fernandes.
Who's for Robin? Raise your hands. Who's for Bruno Fernandes? How many of you support Portugal? Okay, I thought maybe there would be some overlap and a bias, but seems like you're pretty fair. Okay, yeah. So it's not clear, right? You guys are divided. The answer is not obvious. So this is why we need mathematical modeling, especially to help us decide and answer questions when it's not very obvious, right? So okay, let's then discuss how we're going to do that. How we're going to do this sort of modeling. Okay, so let's keep it simple. Let's just look at the x-axis first, right? This is a two-dimensional distribution. Let's not get into that right away. So a few things going on here, but again, can somebody tell me what jumps out from this? Essentially, I'm just drawing out the sort of the representation of the data, but only looking at the x-axis for the moment. And what is this distribution called? Does anybody know? What is this representation? Normal distribution. Why is it called normal distribution? Anybody has an idea? Somebody was here. I heard murmurs. Sorry? Maybe we give somebody else. I heard somebody in this side. The guy who's smiling, maybe. Here, glasses. You, yeah. Next to you. I think you had some idea. Oh, anybody here around this area? Yeah, you. I think you have some idea. Yeah. Yeah. Can you please do it?
I don't know that.
Fair enough, right? No worries. That's what we're trying to learn. that is, if we're here in this room, maybe we are 100 people, something like this. If we were to measure everybody's height and draw like a histogram for what height everybody is, maybe based on like the nearest inch or nearest like maybe a couple inches, centimeters, whatever units you prefer. The distribution often will look like something like this, right? It's shaped like, it goes up in the middle and comes back down, so okay, we're just now. So if we look at the data, like the summary of the data, which we can, so we're basically representing what we see by the normal distribution, and the normal distribution is characterized by mean and standard deviation. How do we compute the mean for the normal distribution or any distribution? Anybody knows? Well, it's mean. You just sum up all the observations that you have, and then you divide by the total number of observations that you have. Quite simple. And standard deviation, you do something. You just take the difference from the mean, and then you square it, and you sum it up, and divide by the total number of data points. So that's how you get a representation. And as we just saw earlier, De Bruyne has both low means, close to zero mean, and low standard deviation. Robin has very low standard deviation, but high bias from zero, high shift from the central value. And the other two guys, basically whatever we compute is sort of represents what we saw earlier, right? So how do we've seen that, we've just said that, we can model some data using the normal distribution, but how do we answer something like who is likely to score? And when we say score, let's just say scoring is like throwing the dart towards the center of the board, right? And that is essentially scoring. Again, we know obviously who is more likely to score, but so now I'm describing how to compute this. I think one thing that is important to highlight is, I think it's quite tempting to think that this is the formulation to use. But can somebody tell me why is this not a good idea?
Bias.
Sorry?
Bias.
Bias? No. So this is not a good idea because this is more of a mathematical thing. It's not something very obvious. But we have two kind of probability distributions, right? We have discrete, well, there are many types, but one general classification is discrete and continuous. And in discrete, when you're modeling into discrete distributions, you can do something like this. There's a value for a discrete value, so for a specific number. When in continuous distributions, this value is kind of undefined, or you can say it's zero. Because in a continuous distribution, there are infinite points, right? So if there are infinite points, one given point cannot have a probability. Does that make sense or not really? Or another way to think about it is, how we want to actually compute the probability is taking area between the area under the curve. That's why, if you remember your calculus, area is represented by integrals, right? For in that domain, integral of the function of interest. You take integral between these two bounds and between these two bounds for continuous distributions. If you were discrete, what should we do? We can just solve. Do you have a question? Huh? Oh, there's behind you. Any questions so far? Okay, so now we have an idea of how to represent your data using some distribution, normal distribution to be precise, and how to compute areas, and then therefore using that to calculate probabilities. Now I'm telling you, now I've computed the area point, right? There's always a range that you can, the bullseye is also a little bit wide. So I'm saying, okay, that area is roughly between negative 0.5 and 0.5. Not surprisingly, De Bruyne is the most accurate, but I hope maybe half of you thought that Robin would be more accurate, but it seems like that is not correct. And the reason being, can anybody give me a reason why Robin is probably so low and why Fernandez seems better?
His mean was
Sorry? Yes, yeah. Fernandez has a higher variance, so it's the same thing, but converse. Rather, Robin is so precise at hitting the left, but he finds it difficult to hit the middle. So and the precision is conveyed by the standard deviation. If we look at this, that peak for Robin, it's very narrow, and at that very narrow peak, he would not be a good candidate to score towards the middle. So it's very important to the concept of variance is very important to understand in sort of almost all of machine learning. You could train a model, right? The model, then we always say the model has either a high variance or a low variance, and we ideally would always want a model with low variance and low bias. And this is an example of what happens when. But then sometimes if your model is quite wrong, then having very low low variance is also bad. So in that kind of situation, maybe it's better to actually have high variance. So that idea is called bias variance trade-off. So I think other lecturers will also be talking about these topics. So again, but then let's not be unfair to Robin. He's a very good player. So if we were specifically targeting the left side, right? If we're specifically targeting this area, then no doubt he's the best. And Anthony, even though his standard deviation is really high, he seems to be second best because he's hitting more towards the left. And Fernandez is better than De Bruyne because, which is again precisely because De Bruyne distribution is so narrow, he cannot hit it too much to the left. And this is obviously there's a flaw in this sort of example. Can anybody point out? Like, if I am asking people I'm asking De Bruyne to hit to the left. I'm sure he can hit it to the left very nicely too. But we're making an assumption that the data, whatever data we have so far, that represents their entire sort of how they shoot the ball or the dart. But obviously you can't infer too much from just 8 data points. This is very silly. You would not do this in real life, but for purposes of demonstration. And similarly to the right, because nobody had a bias towards the right, but because Fernandez had a higher variance, he seemed to be the best if we want somebody to hit to the right. And Robin is like the worst, not surprisingly, and Anthony and Bruyne are also bad. So again, another thing to keep in mind is sometimes the problem, you need to understand what your problem is. Maybe the problem demands you to be targeting to the left or the right. Then in that case, you want your model also be similarly biased. It depends. If you want, and another way to think about that is sometimes, let's say you train a model, you train like a general model, right? If you've trained sort of neural networks, if you've done examples, there's often this standard thing that people do, which is train your model with ImageNet. And anybody knows what ImageNet is? Does anybody? I'm sure somebody. Do you know?
Images consisting of, I think, 1,000 classes.
I think so, something like 1,000, and there's millions of examples. So these are just random images, natural. We call them natural images, like of daily life. people, like animals, nature, like parks, and then oftentimes you train that model. Then that you could say that model is not biased towards anything, has a high variance. Then let's say you can fine tune the model to just recognize faces. Now you made your model biased towards recognizing faces. So this is an example where you do want your model to be biased. I mean, it's okay if your model is not very good at recognizing cats and dogs, but maybe you want it to be very good at faces. That's these kind of ideas keep coming up over and over.
Last one was maybe.
All right. Let's continue. Not sure the slide I'm on, so. Okay, so next up, we naturally want to extend this to higher dimensions because, like I said in the very beginning, it's quite silly to just model the x-axis, right? And we want to now model the x and y-axis together because, not surprisingly, like this, when you're playing whatever football or dart, these things have there's two dimensions to it, right? X and y. Some sports may have third dimension component as well. Maybe if you're thinking about something like basketball, I don't know. Just that thought. So, anyways, but I think whatever generalizes in two dimensions, it generalizes to higher dimensions as well. Well, I have expanded the data set a little bit more. Nothing changes for Dubuina. We just have more data points for him. But for Robin, I have modified like how he's hitting a little bit. So there's a certain kind of pattern to the left and certain kind of pattern to the right, right? So if you see here on the left, he seems to be getting more towards the top, and on the right, he seems to be getting more towards the bottom. I don't think this is reality. This is just the so okay, here's some maybe your first scary math equation for the day, or maybe you already had one in the morning. I don't know. I probably haven't even woken up, I guess. But okay, let's not be so scared. Let's go back here, and that equation is just a generalization of this equation. This is obviously just in 1D. So just remember, here you have some scaling component based on pi and based on the standard deviation sigma. And then you have your exponential term, and you're computing distance from the mean, and you're squaring it, right? I hope you've seen the normal distribution before as well. Now, when we want to generalize this to higher dimensions, it's quite similar, but obviously just a little bit, few things we have to do a bit differently. It is still the pi component scaled a little bit differently. K is the number of dimensions. Now we have a new term here, which is sigma. Sigma is still a representation of variance, but instead of standard deviation, what we need here is we need this thing called covariance matrix. And I'm not going to get into the definition of this. I'll give you some examples in the coming slides, and I think you all can maybe develop some intuitive sense of what covariance means. And then yeah, it's still some kind of like square distance between x and the mean, weighted by and still kind of divided by the covariance matrix. This is the determinant of the covariance matrix. I'm not going to get into the definition of that, but yeah, I think you can find that. But essentially, it's the same thing, sort of just extended to higher dimensions. Any questions so far? Okay, so now instead of drawing a distribution in 1D, we're doing it in 2D. Obviously, in 2D, I can't just draw like a plot. So what I'm doing is I'm drawing contour plots. Are you guys familiar with something like this? Or another term used to describe something like this is called a heat map, right? So let's look at them slowly and sort of try to understand what's going on. So, so De Bruyne is more likely. He seems quite accurate, right? So he seems quite likely to hit towards the zero values, right, towards the center. So I should have drawn a color map here. That would be helpful. But these, just understand that the brighter parts are higher probabilities. So in the towards the center, he's most likely to score because his mean is quite low. It's almost close to zero. So that's why you have these high probability areas in the middle, and it sort of keeps it sort of varies. The farther you go away from the center, De Bruyne is less likely to score toward in those areas. And if you look at the distribution of the green points that I have, the dotted points that I've drawn, these are just samples from this distribution, right? It seems to kind of fit nicely, right? Like these points are sort of mostly concentrated towards the center, and we have less and less of these as we go far away from the center. And another, so any questions just on this? So the mean is now instead of one-dimensional mean, we have a two-dimensional mean for x and y. This is practically zero for De Bruyne because he's very good. Now instead of a variance matrix, we have what we call the covariance matrix. This term and this term are how x and x vary together. So this, you can think of this as the variance of just x, and sorry, this is how x and x varies, and this is how y and y varies. Roughly equal to 1, right? We can just assume, we can just say it's like equal to 1. And whereas these terms represent how x and y vary together. But for De Bruyne, how I'm modeling this is that the x and y, in fact, do not really have any relationship with each other for De Bruyne. He seems to be how he's. Contrast that with Robin, right? What we said earlier is that when your x is towards the left, or rather when your x is negative, y tends to be positive, right? When x is positive, y tends to be negative for Robin. So we say that these x and y variables are dependent for Robin, and for De Bruyne, x and y components are independent. Now, if your random variables are dependent and independent, same thing happens with your probability distribution. The distribution is also independent if your component random variables are independent, and vice versa. What does that even mean? Dependence, independence. I think maybe I'll give some examples later, and why it will become obvious why particularly independence is nicer and easier to model, and dependence is slightly trickier to model. Not surprisingly, because just even drawing this out, independent, because these variables are independent, practically, we will just have to draw these easy circles, right? Whereas here for Robin, we have these complex ellipsoids representing like the variance and the covariances. For Robin, another thing we notice is his throws are not centered at 0. It seems to be at, yeah, it says here, my negative 1.5 and 0.5. So he's biased, and also there's a variance, there's a high variance, and there's also covariance. What that means is the x and y components are related. So one more thing we've introduced compared to earlier. Earlier we just talked about bias and variance, and now we have a third factor, which is also just covariance. So now a little bit some more expressions. So the nice thing, again, I said earlier, nice thing about independent variables is it's easier to model them. And why? Because we can just multiply the individual components, and we will get the constituent, the output joint distribution. Does that make sense? Yes. So go back here. So this just, what this means is if you took all the points here, and if you just took the x components, this is just the standard deviation of just all the x components. That's how you can think about it. This is actually the variance, not the standard, but the variance is pretty practically just standard deviation squared, right? So what that means is if we look at the spread of this distribution for De Bruyne, most of his data points are between -2 and 2. And actually even less so, right? Most of them are actually between -1 and 1. So if we just look at x component. So that's why his standard deviation is his variance is quite low for x, just the x component. Same thing we do for the y. Okay, there are a few outliers here, but let's say we ignore the few outliers. And for overall, even for y, because of the outliers, it's a bit higher than the x. If we only look at the y component, or if we ignore all the x components of these points, this is what this represents. And this represents how they vary together, and not just on its own. How it's related to one another. So can somebody tell me, so same thing here, for Robin, right, it's really spread apart, right? It's going from negative, all the way from -5 to 5. That's a pretty high value, and same thing on the y as well. But the y component is less varied than the x component. If this number, instead of being -3 almost, if it was +3, what would this distribution and data points look like? Can somebody tell me? Instead of almost -3, if this was +3. Sorry? It will be tilted to the other side, right? Yeah. And why so? Right. And it would be tilted roughly, if we were to draw a line there, by the factor of, like a slope of? No, not 1, because probably about 3, I think. Yeah. Definitely not 1. If it was 1, then this value would be about 1. You can think about it that way, maybe not exactly. So the bigger this value is, the bigger sort of this tilt, this stretch is. And another way to think about these is you have points. These covariance matrices also represent, this is. If we assume this is sort of the most normal, basic way how variables sort of vary together in space, represented by a matrix. The covariance matrix shows how how you applied rotations and shifts, scaling to your data. And if you, in this particular case, we've done both. We've applied rotation and we've applied some stretching as well. For instance, now if here this data, right? Now if this data was just stretched, imagine instead of the y value, instead of varying like this, if it's stretched vertically by roughly 2 times this amount, how would the covariance matrix change? How would this component change in particular, the y variance? Somebody said it would be large? Yeah, the standard deviation should increase. It should roughly also double, right? Yeah, so what I did was here I actually did not remove I drew this by taking the small covariance into account. Here I removed it altogether, but I still practically get the same sort of distribution. So we can model, this is how why modeling independent variables is easier in this way. Modeling, and okay, let me also clarify what these terms mean. Oops. So by the way, this is we'll also look at another thing called the Bayes law later, but this is is one way of representing this probability. Probability of x comma y is written in this sort of form. It's x dependent on y times the probability of y. But for independent variables, the x, because there's no dependence on y, we can remove this y term. Kind of like when you're doing, let's say, integration, right? If there is a constant, you can remove that constant. You can bring it in front of the, or same thing with derivatives. You can bring it to the front. You can just multiply it by a scalar. In a similar way, because if there's no dependence, you can ignore this term and then you can write it like this. For dependent variables, we cannot do that. Yeah, so we can write the same expression in different ways, like x dependent on y times probability of y, or y dependent on x times probability of x. But because they are not independent, we cannot like break this down further, and we cannot write this out simply as probability of x and probability of y. So it's not easy to therefore sort of represent this easily. So I again made some random data here. X I first generated x values, and x was simply sampled randomly from the standard normal distribution of mean 0 and standard deviation 1. Then I took y, which is literally just 2 times all the x value plus some small noise, just for like some matrix consistency. Then when you draw this out, this is what it looks like, right? Y is like so strongly dependent on x. That's why you have this almost like a linear relationship. And this is what the covariance matrix looks like. This is standard deviation of x. And y, it's the variance of x. And this is variance of y. Now, does anybody know why the variance of x is 4? Y is 4. Sorry? You had some ideas? Any more ideas on why the standard deviation of y is 4?
X can vary from minus
Okay, I
1 to
can't.
1.
The back had some idea. Now who's hiding? Yeah, maybe we can give the mic.
Here, blue color.
I need more audience participation because I'll run out of things to say. And what are we gonna do? Just stare at the screen? Yeah? You think that's a good idea? I don't think so. Oh yeah, sorry. Some thoughts?
खै मतलब एक मोमेन्टको लागि के भयो जस्तो लाग्यो तर फेरि
I think we have to speak in English first. Because we have participants, non-Nepali speaking participants. Not that I don't like Nepali. So yeah, please, just anything, just give it a try.
the variance of x with respect to x is 1. So I thought, I didn't understand, but maybe it's in terms of the range, it can be thought is minus 1 to 1. Can we say that? And so variance of x in total will be 2. And if we look it in terms of y, then it will be double. So it will be like minus 2 to 2. And that will be 4. I thought like
Yeah, I think you're onto the right thing. But I can say what you just said kind of mathematically.
it's just like variation and variance. Just get.
Yeah. So what about the mean? What do you think would be the mean of y? Not the standard, not the variance.
It's just
the
the
mean.
same. 0. It's a,
So okay, yes, that is correct. But if the mean of x, instead of, I told you it was 0, but let's say it was 1 before. Now what would it be?
If the mean of x,
Anybody else?
if the mean of x was 1,
Yeah. What would be the mean of y? Somebody here? Okay, now I will convey what you said, but let's say mathematically. So, so when you have a variable, random variable x, and if you scale it by a by a constant value, right? The mean is also scaled. The mean is a linear sort of operation. That's why the mean also scales by the same factor. So if the mean of x was 1, then the mean of y would be 2 times 1. But variance is squared by that factor. So if the variance of x is 1, then variance of y would be 2 square 1. Or another example, if variance of x was 3, then variance of y would have been 3 squared, 9, right? Yeah. So the covariance matrix represents variance, not standard deviation. Yeah. Yeah. If you're only modeling just a normal, like a normal distribution in 1D, one dimension. Earlier we were using the term standard deviation, but for 2 and higher dimensions, because we're using covariance matrices, we'll often use the term variance. Although obviously they're related, right? One is just the square root of the other. Yeah. So this is another very important thing to understand. The concepts of independence and dependence. Any questions on the concepts of independence and dependence? Yes. Can we give the mic here, please? Sorry for. Oh, okay, go ahead. You mean this component? Oh, that's just because we said we assumed. I mean, this is the. I made up this example saying the. Okay, x. This is the starting point. I first made a bunch of x points by sampling from the standard normal distribution with 0 mean and 1 standard deviation. But variance is just square of the standard deviation. So if it's 1, the square is also 1. So that's what you get here, and 4 here, and covariance is 2, not surprisingly, right? Yeah, any other questions? Yes, please. If the mean of so your yeah, the picture would just shift, but the covariance matrix would still be the same. There may be some change actually, because it's not passing through 0, and it wouldn't be exactly the. I'm not 100% sure. But I think the covariance matrix would still be the same, because because of the earlier yeah. Any other more questions? Yes, please. It appears as if x is just a one-dimensional value. Yeah, sure. I mean, this is how they write it in sort of textbooks. But essentially x is a vector. And that's why we have vector operations here, like transpose, matrix inversion, and if x was truly a one-dimensional value, like this wouldn't make sense. Similarly, mu, the mean is also same dimension as x. So in our case, x would have been 2-dimensional, and mu would have been 2-dimensional, and sigma would have been 2 by 2. If sigma is 2 by 2, what dimension is sigma inverse? 2 by 2? Yeah? Yeah, of course.
Use your mic.
not power, sorry. It's transpose. Yeah. So, um, yeah, do you know what a transpose operation is? Yeah. If it's a 1 by n, yeah. Yeah. But this operation, I think it's also called a quadratic product. You see these kind of operations in many places. I think more maybe the linear algebra lecture tomorrow as well. This is a very common sort of form that is seen in many places. And this is, you can think of this as just a x minus mu squared and also scaled by the standard deviation. I'm giving hand wavy way to think about it. Because for a moment, think about it like if this sigma was, if your covariance matrix was an identity matrix, right? You guys know what an identity matrix is? Who said yes? Please, somebody. Yeah? Here? Somebody here.
There?
Yeah, identity matrix. Yeah, and the other elements. And why is it interesting? Like in our case, if your covariance matrix was identity matrix, what would happen? Your distribution would look like De Bruyne's shots, right? Yeah, basically this is practically an identity matrix, right? 1 and 1 and 0 and 0, and you'd have like a, I think this is called like an isotropic distribution, which means it's sort of changing evenly, nicely in all directions. So this is the most canonical, standard, basic distribution, like in higher dimension. And if you had, so yeah, I was saying, yeah, if this was an identity matrix, you could just essentially remove this from here, and you would just have like you would just have x minus mu transpose dotted with x minus mu, which would just be like a inner product, which would just mean taking all the individual components, squaring them, and adding them, which is what we. Yeah. So yeah, I am not a I don't work in a university, so I'm not very good at math, but I use like a lot of these hand wavy ideas. I think will help you understand more. And even when I was developing these lectures, I was always drawing it out like this using Python. And I think when I was learning probability, it was all math, and it was really dry and very boring. It was very difficult to learn. And I think these days, with if you use computational tools, and if you do nice visualizations and experiments, I think it should assist your learning even further. So I encourage you to do these sort of things and make nice drawings. And some of you are maybe like more artistically inclined than others, and maybe some of you are just more mathematical, and just like doing the math, and that's fine too. But if you're of this inclination, right, if you like drawing and visualizing, then I think these things are really nice. So I mean, I'm not even good at drawing, but this is my attempt, and I think it's not so bad. I don't know what you guys think, but well, anyways, my point being, when I was learning this in college and grad school, like it was very boring. They were using terrible examples, and I think I have at least it's interesting to some of you, if not all. That's all I'm going to say. Some of you probably don't care about football, and some of you may care and were thinking, why is he drawing dartboards? But well, anyways, this brings me to Bayes' law, and I think this is one of the really foundational equation, law, rule, however you want to think about it, in like statistics, and I'll give some examples later on why this Bayes' law and like Bayesian statistics is interesting. So far, what we've done is we've done this thing called we've used the frequentist approach. If you've heard that term before, and now we're doing some Bayesian stuff, right? So essentially, let's understand what's going on here. I already did something like this earlier. The probability of two random variables can be represented in this two way. It's probability of A given B times probability of about this is there are these canonical examples. Okay, it's like what is the probability that it rains and can somebody give me their let's say her that she carries an umbrella to Nami's workshop today or any given day, right? So that's how we model two random. So there are two random variables here. So let's say A models the probability of rain, and B models the probability of carrying an umbrella, right? So in this case the second expression is more useful. So what is the total, what is the probability then? The probability is what is the probability of rain times what is the probability of somebody carrying an umbrella given there is rain. So it should rain and somebody should carry an umbrella. But somebody carrying an umbrella is dependent on, the dependence is important because carrying an umbrella is dependent on whether there is rain or not, right? Some of you may be too cool and you ride a nice bike, 200cc, and you're not going to be carrying an umbrella. That would just look very lame if you're on your bullet and you're carrying an umbrella. But some of you just take the normal other simple transportation or walk or take the bus. So it's going to be different essentially. Like if it's raining, then you will do something. If it's not raining, so this is why there's this conditional element, and you can depending on the problem, like the dependence could be in the opposite direction, right? There's a reverse, but we'll get into that later. And this is definition of A comma B, and the probability of B given A can be written. It's just arranging this around. Nothing really fancy going on here. But what something like this helps us do is, let's say how this is important is useful is that, let's say I have lecture to do tomorrow as well, but I stay here all night. I don't get out of this room. It may happen, who knows? But I hope it doesn't. And so tomorrow morning, I'm trapped here, and I don't know if it has actually rained outside or not. So I'm just gonna observe people coming into the room, and I'm gonna observe. Let's say it did rain. If a bunch of people carried umbrella and entered this room, then what am I to assume? It's highly likely that it probably rained, unless a lot of people are idiotic, which I don't think is the case. You guys are all very smart to be here. I know this. So essentially, if I'm just sat here and I'm just observing, if 10 people came and 9 people had an umbrella, it's highly likely that you can do the reverse inference, which is, so earlier I said, given that there's a rain, what is the chance of somebody carrying an umbrella? We can also compute the reverse probability. Given that a whole bunch of people are carrying umbrellas, what was the chance of rain? So this is the kind of things that we do using Bayesian statistics. Another important way is if we go back to our Dart examples. So imagine somebody who has never seen football, heard football, watched football, anything. They're like absolute novice, okay, when it comes to football. And they are presented with some data. Let's say they first they're asked to predict what is the distribution of how players shoot football, or let's say darts, however you think about it. Then the idea is that a person will have a prior belief that darts should be. You never have to play dart to have a basic intuition, right? You can easily think, oh yeah, dart is it's this round board. Mostly people probably will hit in the middle, and there's some spread, there's some natural variance. And then you get De Bruyne's dartboard data, and what happens? That assumption is not going to change much, right? But then if that person was presented with raw assumption after that they have seen this data is going to change a lot. So it's we call this idea the notion, whatever the notion this person had before seeing any data, that is called a prior distribution. That's like a belief that the person has about how dart is thrown. And once you're presented with data, you've seen some evidence, you update your prior ideas about how darts are being thrown based on what you've seen. After that update, what you have is a posterior distribution. And if this person was presented with De Bruyne's data, then probably nothing changes. But if this person was presented with Robin's data, then the posterior may look significantly different from the prior. Okay, now I have a slightly different example. Let's do this example. There are two dartboards now, okay, and these dartboards are, let's say, kind of biased, okay. Somehow we have these, or maybe it's not the dartboard that's biased. Maybe the players have. Well, there's obviously something different about these two dartboards because the distribution of the probability of winning is quite different for two different players on the different dartboards, right? So it's like they're definitely biased. So now we want to answer two questions, okay? The board was chosen at random and a game played. What is the probability that De Bruyne wins? Okay? Is that clear to everybody? Second question is, if Robin won, what is the probability that board 2 was chosen? Now we can go back, we can do 1. There's nothing too complex about 1, nothing too complex, but like about number 2, can somebody, without even like doing any computations, what do you think about number 2? So, if Robin won, the probability that board 2 was selected, would that be higher than probability of that board 1 was selected, or higher, right? So that's an intuition you can draw without even looking at without even doing any math, right? But let's do the math. That's what we're supposed to do here today. Okay, so the first one is probability win. I'm using short forms here, but yeah, win equals De Bruyne. And how do you represent that probability? Well, there's two possibilities, right? If there's we have to model both of those probabilities. It's because you can De Bruyne can win in two ways, by shooting on board 1 versus board 2, right? So we have to account for both of those probabilities, and so that's why we just sum it, right? Now let's go back to the definition earlier. Probability of A comma B is probability of A given B times probability of B, right? So basically probability of win given board equal 1 is probability of win equals De Bruyne comma board equal 1 is probability of win equals De Bruyne given board 1 times the probability of board 1 plus probability of win equals De Bruyne given board 2 times the probability of board 2. So now we just do the math, and we get 0.55. So this is nothing too fancy going on here. Like we can just see that De Bruyne stood at overall have better probability of winning because the gap is bigger, right? The probability is greater than 0.5 because here there's a gap of 0.4 and here there's a gap of 0.2. Any questions here? By the way, this first expression is also, I think, kind of mentioned. It's called law of total probabilities. Which is nothing too fancy. It just means, well, you have to account. So win equals De Bruyne means he can win in two different ways here, right? By either playing on board 1 and by playing on board 2. But maybe this problem if we had more boards, we'd have to account for all those boards. So the law of total probability says that all those things have to be accounted for. And we obviously have to add these because these are, why do we have to add these and maybe not multiply? Any intuition there? Yeah, there's another way to think is there's a mutually exclusive events. You can't, board playing in board one, you can't play both at board one and board two. They're independent, right? That's another way to think about it. You either play in board one or you play in board two. That's why you can use or in probability. When it's an or statement, you have to sum. And if it's an and statement, you have to multiply, right? And yeah, we apply not the Bayes law precisely, but we apply the product rule of the two variables, and we get this, right? Now I think the second question is more interesting, right? What is, if Robin won, what is the probability that board 2 was selected? So roughly what this means is we're trying to figure out probability probability of board equals 2 given Robin 1, right? Or another, so this is what we're trying to find out. Board equals 2 given win equals R. So first of all we need to compute both of these components, right? Because we know that we know from Bayes' rule that probability B given A is probability A comma B divided by PA, and what is probability A comma B? It's just it's A given B times probability of B. So we apply the same rule here, and probability of board 2 given win equals R is probability board equals 2 win equals R divided by probability of win equals R. And what is probability of win equals R? Sorry, it's the same, we apply the same philosophy as earlier, right? For the winner. You can win in two ways, it's either board 1 and board 2. Yeah, so then you expand this out. What is the likelihood of Robin winning overall? It's 0.45. And to be honest, you wouldn't have to do this calculation to know the answer. How could you have derived this without doing this computation? Anybody knows?
Go back to it.
1 minus 0.55, right? Because in the distribution of winning, there's only two possibilities, right? In the probability distribution of winning, it's either for any one given game, it's either Robin or De Bruyne. So one of them has to win. So if this is 0.55, we know, okay, maybe I skipped this, but probabilities always have to sum to 1, right? So this has to be 0.45. Yeah, everybody understood that, or some questions regarding that? Yeah, question there.
Why isn't the probability of board 2 being chosen just 0.5? Because board 1 and board 2 could be have the same probability, so why isn't it just 0.5?
Yeah, good question. So if you guys didn't hear, I think what you're asking is why isn't the probability of so maybe you're asking why isn't the probability of board equal to just 0.5? Yeah, sorry, maybe this is the way I've written it. It's looking as if I'm doing this probability of board equal to is this actually, sorry, this is not written very nicely, but this is just a continuation from the above line. This is probability of win equals war. So, but yeah, probability of board equal to is just 0.5. That is correct. But what we are trying to compute is probability of board equal if Robin won, right? If a game has been played, but we don't know which board was chosen. So let's go back to back here, right? Let's say the game has been played. You don't know which board was chosen, right? But I tell you that Robin won. Which board do you think is more likely to have been chosen?
Second.
Board 2.
Board 2, right? Because why?
Because Robin has more chance of winning if board 2 are chosen.
Board 2, right? Yeah, so that's what we're trying to compute. So that has to be, if it's more likely, then it has to be greater than 0.5, right? So essentially, sorry, if this is just a continuation of this line, sorry, this is not equal to this. That was the confusion, but probability of board equal to 2 is different than probability of board equal to 2 given win equals Robin. Is that clear now? So intuitively, is it clear to you? Let's forget about the math for a moment. So if a game was played at random, but we don't buy win equals Robin. Does that make sense? And you can compute this by saying the probability of win equals Robin given board equals 2 times the probability of board equals 2. And we are doing what you're saying. Probability of board equal 2 is 0.5. So yeah, it's highly likely that board 2 was chosen. Yeah, sounds good. Any more questions about this? This is a I think this is a very crucial thing to understand for future talks. I think many fields of ML use Bayesian statistics. Yeah, but yes. Can you ask again?
In the second equation, can we say that there is change in prior belief of winning by Robin, provided that it is board 2?
So you mean here?
Yes. Is there any changing of prior belief?
So there is a change in probability that if you do not have this information, right? Our prior assumption about the boards. What is our prior assumption about the boards? That there's a 50-50 chance of the boards being selected. So now, given that Robin has won, what is the chance that the board 2 was selected, right? That from 0.5 it has been updated to 0.67. So you can think about it like that. But it's not really an update on the entire. If we want to repeat this experiment again, we would again start with the assumption that the chance of selecting board 2 is 0.5, and unless we are specifically trying to update this, which is I'm coming to that also. There's another way of doing it, but so far we're not trying to update the probability of. We're not trying to update this probability. Any other questions? Another concept is the concept of conditional independence. This is also a little bit. Maybe I'll do an example, and we're running out of time. But I think the example will be more helpful than sort of focusing more on the equations. But this is sort of following the same logic as before. Probability of A comma A given B and C times probability of B and C, and this particular simplification stems from this idea of conditional independence. What we mean by that is A given B and C is only, or rather, probability of A comma B given C, A comma B given C equals probability of A given C times probability of B comma C, B given C. So this idea is called, this is the idea of conditional independence. So if we did not have C, probability of A and B would not be independent. But given C, these things are independent. This is also helpful in certain modeling situations, as we'll see. I'll give an example. So these kind of things are often important in situations where when you have a lot of different variables, right? And if you have to let's say you're dealing with 10 different variables, and you have to make a joint distribution of 10 different variables in 10D with a normal whatever distribution, it is very, very difficult to model and understand and figure out what's going on. So these sort of simplifications help us understand these things better. But let's look at an example, right? I copied this from somewhere. I didn't create this. The De Bruyne and Robin examples were mine, but not this, right? This is from some university course in the UK, Queen's University. Okay. So similar to the umbrella and rain example I was talking about earlier. There's the sort of the core event, which is that there may be a train strike, or in our context, let's say we don't have a train strike. Let's just say there's going to be like a bond or something, like a no transportation available. And then there are two guys who come to the office, and there's the two events that may follow is Martin may be late or not, and Norman may be late or not. Now, we're making this joint distribution that there's a train strike. Given there's a train strike, what is the chance that Martin is late, and what is the chance that Norman is late? And this is the distribution, right? So given, if it's true, then Martin is very likely to be late. If it's false, then Martin is very unlikely to be late. This is the distribution probability of t given s equals true, and it has to sum to 1. This is the distribution probability of Martin false given s equals, this is probability of Martin given s equals false. Also has to sum to 1. Similarly, these also have to sum to 1. So it seems like even when there's no like strike or bond or traffic, whatever, Norman's a lazy guy and he's like half the times he's late, half the times he's on time. That's why a strike doesn't really make difference in his outcome that much. Whereas Martin seems to be like a responsible guy. I think in the original example, what was also happening was that Martin actually took the train, so he's heavily affected, and this guy just like drove or something, or did some other method of transportation, and yeah, he wasn't really affected. But also, yeah, he's a lazy guy. We know that, right? And the probability of strike is, not surprisingly, it's not going to happen all the time. It's 0.1, 0.9. So the first question, what is the likelihood of a train strike but both Martin and Norman not late? So what is this probability? But now we have three things, right? But three different random variables we're using. So we're using this idea of conditional independence here. We're saying the Martin being late or not late and Norman being late or not late they're independent. That's why we're multiplying this. But given that it's conditioned on the strike, right? So we do this multiplication, and now think about it. Does this make sense? There's a strike and both Martin and Norman is not late. This has to be really low, right? Because this is low and this is low. So when there's a strike, the highly likely scenario is they're both going to be late, right? And not the opposite. That's why this probability is really low. Does that make sense? Now we're going to do the Bayesian stuff. It's the same thing as before. The darts, it's just expanded. It's just, now we have three variables. So basically, the question is, what is the likelihood of a strike given both Martin and Norman are late? Now, okay, what do you think, without looking at the answer, what do you think the likelihood of strike given they're both late should be? Should it be closer to 0.1, closer to 0.8? Should it increase from 0.1?
Yes.
It should, in all likelihood, it should increase significantly, right? Because we're observing that they're both late. And okay, this guy, Norman's not very reliable, but if Martin's late, then it's quite likely that there was probably a strike, right? So that's why, yeah, we do this computation, and we again use the idea, it's the same thing as before, where first we need to compute this lower part, the m equals t, give times n equals t. And this can happen in this summation, this can happen, we need this probability, but this can happen when s equals true, but also when s equals false. We need this, that's why this computation is a bit long. We get this probability. We get the probability that Martin is late and Norman is late, and we need to sum it for both false strike and true strike. And probability, and then this probability is already computed here. I didn't have a lot of space, so I'm just reusing. So it's just the total, the answer is this divided by 0.093, which is 0.53. So that's So yeah, I mean, this is the kind of these are just discrete examples, and this is basically power of Bayesian analysis. It helps us like make inference about things, update our belief about things. Yeah, I don't want to spend too much time now. There's this idea of marginal distribution. Actually, what we did here is essentially we marginalized our distribution. We removed this is called marginalization. Our probability distribution is also dependent on S, but we wanted to remove the dependence on S. We wanted to find the distribution only for m equal m comma n. So in that case, we need to do the summation across all the values of possible S to get this distribution. This is exactly what we do here. Probability of X is if the marginal distribution of X is this function, and you integrate out Y basically. For discrete case, we just did it. I'm not going to spend too much more time. I can go show you an example. So we're back to De Bruyne and his start. It's probably the last time, right? I think we've had enough, but maybe not. Maybe there's some more surprises later. So yeah, I'm just simplifying a little bit. I'm making it discrete. These are his x positions, and these are his y positions, and this is your joint distribution. You don't need to do it, but I purposefully built this so that you add all these up, it sums to 1. Then what we can do is we can compute marginal distribution. What that means is for y equals -2, if you sum up all these probabilities, you get the probability that y equals -2. Sum up all of these, you get probability y equals -1, so on and so forth. Similarly, you sum across the rows for x equals -1, you get the probability x equals -1, and so on and so forth. And you sum up all of these, because that's a proper probability distribution as well. This is also 1, and this is also 1. So yeah, basically, this is necessary to do those computations, step of marginalization. Now, the final thing that I wanted to mention is this update. Somebody had asked earlier, are we updating the prior, the chance, the likelihood that the board, the probability of the board being selected was 0.5. So this is the kind of thing we do to do that kind of update. There's a proper method for that. We compute the likelihood that the observations drawn from this distribution, what is the likelihood for that, and then the probability of theta given x is just using the Bayes rule, probability of x comma theta divided by probability of x. This is this Bayes rule that we saw earlier, right? Now the one thing that you may see in other lectures and in future in other domains is that oftentimes it's hard to, continuous variable, hard to compute this value. There's all kinds of integration and complex math, which, like I said earlier, I'm not very good at. But oftentimes we only care about the top part and not this bottom part, and we only care about the part where this theta has a maximum value, and we estimate this maximum value by just maximizing over the numerator. And this is called maximum a posteriori distribution, maximum a posteriori estimation. Now, if here you did not have this p theta component, it's called maximum likelihood estimation. So you'll hear these terms in the future in other lectures and maybe other domains, machine learning or stats or whatever you guys end up doing. So yeah, keep these things in mind. Yeah, I don't expect you to understand this in 1 minute, but this is maximum a posteriori distribution, and yeah, if we didn't have this theta component, that's your maximum likelihood distribution. So yeah, I use this idea of update, and basically I assume the prior distribution was normal 0 and 1, and I generated 8 samples of data points, and after that, the posterior distribution for Robin, after using Robin's data, was shifted to like -2. And for Anthony, where this guy is like all over the place, the shift is is not so strong because his values are not very certain. So the variance is, it's important to, for normal distribution, there's actually a closed formula for how to do this update. I didn't do that, but for Anthony, it did not update much because Anthony has a much higher standard deviation. Now if our prior was very strong, right, what that means is if we have so strong a belief that it's absolutely zero, there's absolutely no room for error, it has to be this. Then for both of them, the data does not change the prior. For Robin, it moved by 0.2, and for Anthony, it only moved by 0.04. So again, even here, the idea of standard deviation is an important concept, and variance and so on. I think this may be it. All right, any questions?
Could you move to the slide just before the train example?
Here?
No. Yeah, this.
Here?
So, why did that B disappear from going from second line to third line?
Second to third?
Why
Yeah.
did the B disappear?
Yeah. So this is exactly the idea behind conditional independence, and also, so let me use a different example. So let's say, so there's this idea called Markov chain. So we don't need to get into that, but let's say you have a bunch of random variables, okay, and they are let's say you observe. Okay, let's talk about the rain example again. Let's say you want model probability of rain, but by looking at data from 5 days, like 5 days prior until today. Okay, and that seems like a reasonable thing to do because what happened a few days ago probably affects what's going to happen today, right? But let's say you also happen to have data. But okay, let's say you do some math computation and you find out that actually and the way to write what the correctly express that is probability of rain today given you use this symbol given rain yesterday, day before yesterday, and 4 days, let's say 5 days prior, whatever this math. So that's how you write it out to start with. But let's say you collected a lot of data and you figured out that, oh, actually what happens day before yesterday, the day before yesterday, 3-4 days prior is absolutely useless. It turns out that you only need the data from 1 day before. So then what you do, you can simplify your expression to, you just remove all the terms that there is no dependence on, and you just make it like this. So it's a similar idea, this idea of conditional independence. So given C, because the idea is that given yesterday already captures information about what happened before yesterday, and so when you're doing this computation for yesterday, you've already incorporated information from day before yesterday. Does that make sense? So you only need to look at 1 day before. I mean, I'm not saying that is the truth. I'm saying it may turn out to be that.
So the assumption is that C captures the information of E.
Yeah, so it's like, what is the probability of Martin being late, given Norman being late, and there was a train strike. Okay. Now, if I had told you, if you don't know anything about the train strike, probability of Martin being have seen this, right? The numbers. Sorry. If Martin is late, and if there was a train strike, well, that's not the train strike. There is a correlation, right, between what Martin's. It's a very small correlation, but when Martin is late, Norman is also more often late. When it's true. Sorry, yeah, 0.6. It's not 0.5 and 0.5.
Yeah, so there's a high.
Yeah, so it's a little bit high. There is some correlation. But then, as soon as I give you information, there was a strike or not strike, you don't need to know whether Martin was late or not. You can just infer. You can say what's happening with Norman by just looking at the strike situation. But if you did not have access to the strike information, you would draw inference from what happened to his colleague. So it's this idea that given that you have this strike information, you don't need to know anything about his colleague. Does that make sense? Roughly, okay. Let's work with that for now. And
Thank you.
which field? Everywhere, obviously computer vision, machine learning. So in machine learning, if you are doing, let's say there's this thing called Bayesian models, where you also estimate the uncertainties of your predictions. Then you need Bayesian analysis. It's used a lot, like in medicine, I think. Because let's say you're doing some kind of diagnosis, then you can model your variables using these relationships. Let's say you look at a patient and you've done X-ray and CT, and you want to make a diagnosis based on X-ray, CT of the same organ, let's say the chest. But if you've already done CT, the X-ray is redundant, so you can throw away the X-ray component. You can simplify your model of how to do a diagnosis, right? So these sort of ideas. I think it's used in a lot of places, but I think you hear from other speakers who are from different